now let's get started on 10.3. This is the integral test, and we'll talk about p-series. So this is when we first start developing basically tools to determine if these infinite sums or infinite series converge or diverge. So before we get started on that test, let's look at this theorem. So and remember, if you leave off the indices like that, then indexes, then it's assumed it's infinite. So if the series a sub n is a positive term series, that means every a sub n is greater than 0. And if there exists an m greater than 0 such that S sub n, which is the partial sum, is equal to that, is less than m for all n, so n is equal to 1, 2, 3, etc., then the series converges and has a sum less than or equal to m. If no m exists, then the series diverges. All right, so let's look at the proof of that. If S sub n is a sequence of partial sums of positive term series, right, then S sub 1 is less than S sub 2, etc. And if that's the case, when you're making those sums, remember it's a positive term. So when you add up terms, it's going to increase. And then it's monotonic. If there exists an m such that S sub n is less than or equal to m for all n, then the sequence is bounded and monotonic. And we know from the previous theorem that a bounded monotonic sequence converges. Right? Therefore, the limit of S sub n, remember it's the sequence of partial sums, is equal to S as n approaches infinity, which is less than m. And then it goes on to say if no m exists, then it diverges. So it's like showing somehow that there's an upper bound, is what that's really called. If you can find an upper bound m, and you know the sequence is monotonic, remember it's the partial sums, then you know it has to converge. So we're going to use that theorem in this integral test. So theorem 9 or 9.1 is called the integral test. So this is when we'll be applying this one. If f is if f, the function f, is positive, continuous, and decreasing for all x, and note that it's greater than 1, so it's like after 1, and a sub n equals f of n, then the series and the integral, it's the improper integral from 1 to infinity of f of x dx, they either both diverge or both converge. So either both convergent or both divergent. So you're going to use this summation. Remember, the integral is basically a summation. So this summation of f, which is exact, is you can show that they're either both convergent or both divergent. So instead of showing that the sum converges or diverges, we show that the integral does. So this proof is different from your book, although it's similar. You don't have to go memorize it or anything. We just want to go through it a little bit. So take some time to read through that, and I will describe it as we go. All right, so zoom in a little bit. So we state the hypotheses up here. Okay, n is positive integer greater than 1. And first, what we basically look at are these inscribed triangles like this. So all these rectangles are inside the curve. So we first look at that, and you get this sum. And note you're starting at 2. Okay, so it's starting at 2. Okay, then you have the circumscribed rectangles, or the polygon, so it's this one. It's either on the outside, and you have this sum, and you're going up to this value here, the f, the n minus 1. So what you get then is you get that the integral is between the outside and the inscribed summations. So if S sub n is the partial sum, then we can rewrite this sum in this way. And that takes a little bit to see why that works and why the notation and subscripts work. Just you got to study that a little bit. So the inequality implies that the integral converges or equals k. So if this does converge, then you have these two possible. You have this S sub n minus f of 1, because it's one of those, is less than k, or you say S sub n is less than or equal to k plus f of 1. So by the theorem above, you can show that the sequence of partial sums by this is less than a constant. So it's k plus of another fixed value. And it's monotonic, so therefore it converges. So I went through that quickly. It takes a little time to study that, but that's the concept. Okay, so take a look at that some more. It's good. It's a good one to study to see how things work. So let's go on then to an example. Determine whether the infinite series here converges or diverges. So usually when we ask these questions, we'll say use the integral test, because otherwise you wouldn't know necessarily when to use it. So we'll generally tell you to use the integral test when necessary. So since a sub n is equal to n e to the negative n squared, we can let f of n be n e to the negative n squared. Okay, and then we consider the function, right, the real valued function, f of x, x e to the negative x squared. So this is the function we're going to use to integrate. Okay, so then if x is greater than or equal to 1, f of x is positive. That one's clear, right? Because e to the x, e to anything is always positive, and a product of a positive is still positive. So f of x is positive and continuous. But my little asterisk here is showing or stating basically we must confirm the hypothesis of the test. So the hypothesis of the integral test is back here. If f is positive, continuous, and decreasing, so you have to show that that function is decreasing. You have to, if it's obvious, you got to state it, but this one's not obvious. You need to show this. So now we need to show that f is decreasing. So how do you show something's decreasing? We can find the derivative. So if you can show that f prime is always negative, then you know it's decreasing, right? So you want to show basically the function's doing this, and then the slopes right here at every point, right, are always negative. So we want to show f prime is negative. So we got to take the derivative of that function and interpret it. So that's what we'll do. So since f prime of x is equal to, and then you have to do product rule on that. So its derivative of x is just 1, so it's e to the negative x squared minus, hold on a second, I gotta move this down. So you get 1 times e to the negative x squared minus the x times the derivative of e to the negative x squared, which will be negative 2x squared e to the negative x squared. Then we can factor out e to the negative x squared. Then we're left with 1 minus 2x squared. So we know that e to the negative x squared, or e to anything, is positive after 1. Well, it's always positive. And so remember that we're saying after x is greater than or equal to 1, then we're subtracting. So it's 1, and then we're subtracting 2 times something greater than 1. All right, so in that case, this will always be negative. So that is always less than 0, which is what we want to show. So since f prime is less than 0, f is decreasing on the closed interval from 1 and then approaching infinity, which is exactly the hypothesis that you need to show. You need to say f is positive, continuous, and decreasing on 1 to infinity. Once you do that, you can apply the integral test. So we may apply the integral test. And so you need to take the improper integral, indefinite integral, from 1 to approaching infinity of x e to the negative x squared dx, which is equal to the limit as t approaches infinity, integral 1 to t x e to the negative x squared dx. So that's just a basic u substitution where you get the x. So you go ahead and work that out, what that limit is. Or not the limit, sorry. Go ahead and work this integral out and pause it. And so you get the limit as t approaches infinity of, and then it ends up being negative a half e to the negative x squared. And you're evaluating that from 1 to t. So you can factor out a few things and simplify, but you end up getting negative a half times the limit as t approaches infinity. And then it's substitute in your t, 1 over e t squared minus, not 6, 1 over e, right, e to the 1 squared, which is just 1 over e. And then if you take the limit, this, of course, goes to 0. And so you end up with a negative a half times the 1 over e. So it's just positive 1 over 2e. So it's equal to positive 1 over 2e. And so this converges less than infinity. So therefore, the sum a sub n converges. And that's by the integral test. So it doesn't tell you what it converges to, and they converge to different things. Like the summation, be clear on this, the summation does not converge to 1 over 2e, all right? Because you're adding up you're adding up infinite terms, but it converges to something completely different. They just happen to both either converge or diverge. Okay, so that's a good example of the integral test for something you have to show that f is positive, continuous, and decreasing. So now let's look at using the integral test for a p-series. So this is, we're going to first define the p-series and then look at that. So here's a definition of p-series. So we've already talked a little bit about this. You may have seen it here and there, but a p-series, or sometimes called a hyperharmonic series, we'll just call it p-series. P-series is a series of the form, so it's the sum as n goes from 1 and then to infinity, approaching infinity, 1 over n to the p, which is equal to 1 plus, right, we just write this out, 2 to the p, etc. 3 to the p, and then you have your general term, and then etc. Where p is a positive real number. We're not looking at the p being negative. That would obviously not work because it wouldn't go to 0. So for every p that's positive, 1 over n to the p does approach 0. So it's not going to diverge by the nth term test. So the question is, when does this series converge or diverge? And we mentioned in previous lectures / videos that the harmonic series 1 over n diverges. We proved that. So that's like the pivot point when it converges or diverges. So that's going to be the theorem. Sorry. So here's a theorem. I'm not exactly sure the theorem in your book, but it doesn't matter. So this one says the p-series, which is the sum n from 1 to approach infinity of 1 over n to the p, and it has two cases. It converges if p is greater than 1. Right, so you're raising n to a higher power, like 1.5 or 2, and diverges otherwise. And then 2, the series diverges if p is less than or equal to 1. So we can apply the integral test to prove this. All right, so let's take a look at that. So we'll call it a proof. All right, so then what we have, we'll do basically this case. What we're going to look at then is this function. We're going to let f of x be 1 over x to the p. All right, and then where p is greater than 0. So for now, we're going to leave off some of the details. I want to just show you what the integral does. So if you take the integral, so look up some of the details in the book. Okay, so it's positive, decreasing, and all that. So and continuous. I'll just state it right here. How about that? So just say is positive, decreasing, continuous. So you do want to look at this case pretty good, though. This gives you some understanding of why the series converges or diverges. So if you look at that integral, you get the limit as t approaches infinity, integral of 1 to t And then is x to the, say, negative p. How about that? Dx. So that's the limit as t approaches infinity. And then it's x to the 1 minus p, right? You're just applying the power property for integrals or antiderivatives. 1 to t. So that's equal to 1 over 1 minus p times the limit as t approaches infinity. T 1 minus p minus 1. So take a second to see why that works. So we would need to analyze this now and see what occurs. So what happens of the coefficient here, the 1 over 1 minus p? So you have a couple cases. P is greater than 0, so we know that. It's not going to be negative. What happens if p is less than 1 versus p greater than 1? All right, so let's take a look at those cases. All right, so if p is greater than 1, then we have p minus 1 greater than 0. And we can write this as 1 over 1 minus p times the limit as t approaches infinity, 1 over t to the p minus 1 minus 1. And this is equal to 1 over 1 minus p, 0 minus 1, which is equal to 1 over p minus 1. Okay, which converges. Okay, so therefore, since that converges, the sum converges. All right, so now let's look at this. If 0 is less than p is less than 1, then we have 1 minus p is greater than 0. And we have this limit. We have 1 over 1 minus p times the limit as t approaches infinity, t to the 1 minus p minus 1. So in that case, see how this coefficient's kind of irrelevant, right? Whatever happens here, but we're looking at this. So this whole thing is going to approach infinity, and minus 1 doesn't matter. So that's equal to infinity. Okay, so therefore diverges. Okay, so I went through that kind of quickly, so spend a little time on that to see how that integration works. So we'll look at a couple examples and move on from that, a couple of illustrations. And we'll look at and develop more convergence